Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the boggle board. This is a really cool question. It's really complex because it involves a lot of different data structures and sort of concepts, but it's really important to get this question. It'll teach you a lot, and the solution that we're going to come up with is going to be very, very clean. And it's going to put all these sort of concepts and data structures together in a very clean and elegant way. So without further ado, let's dive into it. This question gives you a boggle board, and we'll explain what that is in a second, which is going to come to you in the form of a two-dimensional array or a matrix filled with letters. So in front of me, I've got a boggle board with a bunch of letters in it. You're also going to be given a list of words, and these words are just going to be, random strings of characters. In our case, we're going to be dealing with English words or quasi-English words. So I have an example list here on the right. This is not, etc. And you want to write a function that is going to return another list of words containing only the words from the list that you're given that are also found in the boggle board. Okay? Now, for a word to be found in the boggle board, it has to appear with, all of its characters sort of in order, but all of the characters have to be adjacent either horizontally, vertically, or diagonally in the boggle board, right? So they can kind of be like weirdly positioned so long as they are adjacent in one of those three ways in order. And you cannot reuse a character at a given position more than once. So for instance, in the top left corner here, I've got the letter T, right, in the top left corner of the boggle board. If I had a word that had the letter T twice in it, I wouldn't be able to use this particular letter T in the top left corner more than once. Okay? So you have to use different characters at different positions. That's kind of the caveat of this boggle board. So for this example in front of me, all the words written in purple, like this and is and a, simple, etc., are actually contained in the boggle board. The ones written in white are not contained in the boggle board. So let's look at the ones that are contained. We look at this. We can immediately see it. It's kind of at the top here. This is a, and by the way, you'll notice that is already appears multiple times, right? If I undo these lines, we can see that is appears here, is appears here, is appears here, right? It starts here with this I, and then it moves to this S backwards. That is correct, right? Here we've got is from the word simple, starting at I here and going to S here. So you can have a word that appears multiple times in the boggle board, but you only want to return it once. So going back to the lines that I was drawing, we've got this, we've got is, a, we've got simple here, then we've got boggle here, right? So kind of funky looking here, going diagonally down and diagonally up. Then we've got the word board, like this. Board. So that one's another kind of funky one. And then finally, where it gets really interesting is when we start dealing with repeated characters. At the very bottom, right, you see how we've got this word not re-peated. We can see it's here, right? Not re-peated. And then it kind of goes backwards. The string repeated, however, isn't in the boggle board because we can see it here in the middle, right? It sort of looks like it's here. But if we follow the trail of characters, right, we've got R, E, P, E, A, T, and then we need another E before we can hit this D here, right? And the only other E that we have is right here. We've already visited it. So we would have to do something like this, right? Going that way. But we cannot repeat this E. That goes against the rules of the boggle board. So that's why this string repeated here is written in white, and it's because it's not going to be contained in the boggle board. So that's the example that we have. Let's undo all of these lines. And now let's try to figure out how we can actually solve this problem. Immediately, you should realize that this is going to be a tough problem. It's going to be a complex one, right? You could naively iterate through all the characters. At every character, iterate through all the words in the list of words that you have. Check if the character is equal to the first letter of any word. Grab all the words that have a first letter equal to the current letter that you're at. Store them temporarily in some other list. Then you start going to the second character and you iterate through all of them and you see if their second character matches. And you can quickly see that you're going to be doing like a ton of iterations through lists of words, iterations through characters, and you're likely going to have a very suboptimal algorithm, or at least an algorithm that has a terrible time complexity. So we have to take a step back and start to think, how can we use, or are there data structures that we could use that could make this a lot simpler? Okay. And in fact, what we can first do is actually divide our problem into two separate problems. Because if you think about it, there are two separate problems here, right? One of the problems that we have is to actually traverse this boggle board to construct words, right? So if we start at the letter T in the top left corner, we can either go to the right, right, to do like this. We can go diagonally, TI. We can go to the bottom, TS, right? And so that's one problem. Actually traversing this boggle board and constructing words out of it. And that's likely going to be some kind of graph traversal problem, okay? The other problem that we have is actually matching these characters to our list of words, right? How do we, as we're traversing the boggle board, how do we very quickly and efficiently match the characters that we're at to characters in these words that we're given, and in such a way that we keep track of the words, right? That we keep track of the words that we're, sort of constructing through the boggle board. And so that's where I guess I'm going to directly dive into the optimal solution. That's where we can make use of a tree data structure, TRIE. And so I'm going to make a quick pause here and say that if you're not familiar with trees, I would highly encourage that you check out the suffix tree construction question that we have right here on algoexpert.io. It'll cover everything you need to know about trees, specifically suffix trees, but that's kind of like a more specific example of a tree. And moving forward in this question, I'm going to assume that you are familiar with how trees work. So if you're not, go check out that question. So we can build a tree that's going to hold all of our words. And the reason that this should kind of come to mind is that typically when you're dealing with a bunch of strings and you have to somehow do some sort of string matching with regards to those strings, trees tend to come in handy. They tend to be really good. They tend to lend themselves really well to these types of problems because they make accessing various characters from multiple strings really easy, right? So if we dump all of these strings in a tree, I'm not actually going to build out the entire tree, but I'll build out a couple of its branches. You can imagine that at the root node, right? At the root node, it might have, or it would have, I'll write it in white, it would have the letter T as one root node, or one node in the root node, because we've got the word this and we've got the word test, both of which start with a T. And then this T would point to an H for the word this, and it would also point to an E, because we've got an E in the word test. So this would point to an H and an E. Then this would point to an I, this would point to an S, this would point to an S, and this would point to a T. And then here, since we would have the end of two words, both of these nodes here would point to an asterisk or some kind of, end symbol denoting the fact that we've got a full string here. And we might even store the full string here. So for instance, we might store this here and test here. Okay. Similarly, we would have in the root node, we would have the letter B, because we've got boggle and board. So we'd have the letter B. Then the letter B would point to the letter O, which would actually be shared by both boggle and board. And then we'd start to branch out, right? We'd have here the word boggle, so G, G, L, and then E, and then an asterisk. And then here we'd have an A for board, R, D, asterisk. Okay? So here, again, I didn't build out the entire tree, but I just gave you an idea. If we were to dump at least 4 of the words in our list of words, this, boggle, board, and test, we would have this as our tree. Okay? And so what that means now is that we can do this sort of string matching as we traverse our boggle board very easily in constant time by using this tree. For instance, if we start at the top left corner, right, we're at this T in the top left corner of the boggle board, we can just say, instead of having to iterate through all of our words to say, oh, which words starts with the T? We iterate through the first one, we've got this, no, 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 this, no, no, right? Instead of doing that, let me undo all of that. Instead of doing that, we can just say, is T in the root node of our tree? Yes, it is. Okay, great. We've got like a potential word. So, let me redo that. So we're going to dive into this T now. We're going to forget about all the other levels in our root node or in the root level of our tree. We're going to dive into the T node. Now we're going to look at all of the neighbors, and I'll dive into how that works, how that portion of the algorithm works in a second. But we're going to look at all the neighbors of our T in our boggle board and see if any of them is actually contained in our tree here. So, or in our tree level, which is at this T right now. So, is this S contained somewhere here? No, it's not. Is this I, which is diagonally connected to our T, contained somewhere here? No, it's not. What about this H? Oh, the H is, right? Now we can dive one level deeper into the tree. And these are all constant time operations, right? Like checking if T was at the root level of our tree was just, accessing a value in a hash table. And then checking if H, I, or S were in our tree at this level was similarly just accessing a value in a hash table and seeing if you got anything out of it. So that's that allows us to very easily do this string matching. So now, after the H, we can see that, this I is contained here in the tree, so we can dive deeper into it. Then this S is contained, and now, we've got an end symbol, so we know that we've got a string here, and we can add the string this to our final list of words that we're going to return. Okay? So that is one portion of the algorithm. Build a tree out of our list of words by just dumping them in the tree. And then as we traverse our boggle board, which we're going to cover now, we check if any of the letters that we're at are contained in the current level of the tree that we're kind of traversing. If they're not, we'll forget about it. If they are, we dive deeper into the tree and we check if there's an end symbol to see if we've got a string constructed. Okay, so now how do we actually traverse this boggle board? Well, on the one hand, we shouldn't complicate ourselves, right? We know that we're going to have to traverse it somehow. So we're going to have to iterate through all the characters, right? Because every character in this boggle board is a potential contender for the first character of a word in our list of words, right? So we have to iterate through all of these characters at least once. But then once we find a character that is located in the tree, because I guess at this point you've probably guessed it, right? We iterate through all the characters, and at each character we say, oh, is this character in the root node of our tree? And if it's not, just skip it, because that means it's not the first letter of a word. But if it is located in our current level of our tree, and it is the first letter of a word, what do we do then, right? Well, we know that we have to find a second character that is adjacent to it, either vertically, horizontally, or diagonally. So that tells us exactly where we have to look to find the potential next character. We just get the sort of neighboring node. If we treat our 2D array or our matrix as a sort of graph made up of nodes, where each node is an element in this matrix, well, we look at all of the neighboring nodes, right? If let's say we're looking at this B character here, which is going to actually be the first letter of boggle, right? Like this. This B has 5 neighboring nodes, one above, one diagonally above, one to the right, one diagonally to the right, and one below. Okay, so for every node, if we find that the value of that node, the character or the letter stored at that node in the top level of our tree, we can say, okay, let's start looking at our neighboring nodes. Okay, and for the neighboring nodes, we do the same thing. We check, is that neighboring node in our new current level? So let's go through the example with this B, right? We start with B, and we say, is B in the root level? Yes, it is. Let me undo all of this. Is B in the root level? Yes, it is. So we can dive into this level of the tree, and now we look at all the neighboring nodes of B. We start with the S, right? We say, is S in this level of the tree? No, it's not. Okay, let's look at the I. Is I here? No, it's not. What about the X? Is X here? No, it's not. And then the O. Yes, the O is here. Okay, so let's dive deeper. We dive deeper, and now we're in the O. And this is where now things get tricky, right? Because how many neighbors does O have? O has 8 neighbors. Now I'll use a purple pen now to denote the neighbors so that we don't get confused. It's got neighbors, in the top left, immediately above, top right, bottom left, left. 8 neighbors, right? Now, as humans, we can see that 7 of those neighbors should be, further explored and traversed, and there's going to be one, the G, that's going to be the correct one. But there's one neighbor, this B, that we shouldn't re-explore because we just came from it, right? And we're not allowed to repeat characters. And this might seem obvious here, and you might say, oh, it's trivial. Just keep track of the character that you just came from. But imagine, like, instead of the characters being like this, we had the second G here, then an L here, an E here, right? So we did like boggle. And imagine at the end of boggle, we had a B. So it was boggle B. That was the string we were looking for, right? By the time we'd be at this E, we'd be very tempted to explore the B here, which was the B that we had already kind of traversed at the beginning. In other words, we would not be allowed to use this B again. But so if we sort of just naively kept track of the character that we just came from, right, or the node that we just came from, we wouldn't be aware that this B had already been traversed. So we have to do better than that. We have to keep track of nodes that we've already sort of visited, but in a better way. So let me undo all of this. So what we're going to do is we're actually going to have, is I'm going to undo all of that. We're actually going to have a completely sort of separate or auxiliary data structure, which is going to be an array or a two-dimensional array or a matrix of the exact same dimensions as our boggle board. And this auxiliary matrix is going to keep track of all of the nodes that we've visited so far, but not so far in the algorithm, so far in one sort of exploration branch of the algorithm, right? Because when I explore boggle here, even if it, like, imagine, or let me rephrase. When I'm exploring this B here, I might start by exploring BX, right? And I'll say, okay, X isn't correct, so I'll mark it as visited. But then when I go down to boggle, right, I should still explore the X because we might have the string box in our list of words. So what I'm trying to get at here is that for every branch that we're exploring, only for that branch do we want to keep track of the things we've visited before. Anything that we visited in another branch, like, BX or BI or BS, we don't want to mark those as visited when we're going through this branch boggle, right? Because when we're going through the branch boggle, the S up here has not been visited, not in the branch boggle. Okay, so that's really important to realize. And so what that means is that if we kind of implement this algorithm with a sort of depth first search approach, and here again, if you're unfamiliar with these kinds of graph traversal methods, I'd really encourage you to do some of the more the easier questions on algoexpert.io in the graph category, depth first search, breadth first search. Make sure you're really familiar with those. But so if we go with the breadth first search approach here, we're going to want to have this auxiliary matrix that's going to keep track of visited nodes to update itself and sort of mark nodes as visited, but then back to unvisited as we finish exploring branches. Okay, so let's actually go through an example. So let me undo all of this junk that I wrote here. And let's actually say that we start at the top left corner with the letter T, okay? And what I'm going to do is I'm going to mark nodes as visited by just writing a V above them. But know that in the algorithm, we're actually going to have like a separate matrix, as I just said before, that's going to store some kind of Boolean value to represent whether a node's been visited or not. Okay, so we start at the letter T. The first thing that we do is we check, wait a second, has this letter been visited? And because it's the first letter, of course it hasn't right now. So now we check, is this letter in our tree, in the root level of our tree? Yes, it is, so we can update our current level of the tree to be here at the T node. Now we want to check, is there an actual string here? Like, does this T point to an N symbol? Because if it did, imagine that we had an N symbol. That would mean that we'd have the letter T in our words. We'd want to store that, right? That's just a little reminder that we're also checking whether or not we've constructed a valid string. But here there is no N symbol. So we start exploring the neighboring nodes of our T node. Now, getting the neighboring nodes, as you can imagine in the actual code implementation, we'll probably have a method that grabs all of the neighboring nodes and does some kind of check to make sure that we have valid neighbors. Like here, if we're in the top left corner, we only have 3 neighbors, so we want to make sure that we only access these 3 nodes and we don't try to go outside of the matrix. But once we've grabbed the 3 neighbors, let's assume for the sake of this example that we're going to visit them in a depth-first search approach going clockwise, okay? So the first neighbor that I'm going to visit here is going to be the H, okay? Now, before I visit the H, because T was in our tree, I'm going to mark it as visited. So now I'm actually going to mark T as visited. And now I'm going to go to H. And I'm going to say, first of all, is H visited? No, it's not. So we're good. Is H in our current tree level? Yes, it is. It's right here. So let's go deeper in that. Let's mark H as visited now. And let's continue going in a depth-first search way and explore all the nodes, all the neighboring nodes of H. So because this is depth-first search, right, we're forgetting about the other neighboring nodes of our first node, the T. So we're forgetting about this I and this S. And now we're going to look at the neighboring nodes of H. It so happens that H also has I and S as neighboring nodes, but they're neighbors with regards to H, not with regards to T. What that means is that when we explore these 2 neighbors, they're going to count H as visited. When we explore them coming from T, they're not going to count H as visited. And afterwards, we're going to be able to explore H from them. Okay? So let that, if you need to, maybe pause here and try to let that sink in to really understand that. Okay, so H is in our tree level. We check if there's an N symbol to see if there's a string, just TH. There isn't. So we move on to the neighbors of H, right? So we're going to have 1, 2, 3, 4, 5 of them. We're going to go clockwise. So we'll start with I. So circle I. Is I visited? No, it's not. Is it in our tree level? Yes, it is. So mark it as visited, and now we continue in the depth-first search approach and explore I's neighbors. And by the way, there is no N symbol here, so there's no string here. Okay, we go clockwise, we go to this S. S is not visited, it's in our tree level, mark it as visited. And now we check if there's a word, and there is. There is an N symbol in our tree, so we can say, okay, this is an actual word. And by the way, again, this is where constructing our tree in such a way that the N symbol actually maps to the string that we came from is going to be really helpful. Because that means that we won't actually have to keep track of the characters that we were traversing to construct our string. We'll just have it here at this N symbol that we're already accessing easily. But okay, so we've created a string, but that doesn't mean that we stop now, right? There could be another string that could be this I, right? That could be a string in our list of words. So we're going to move on to the next neighbor. So this is going to be this I. Is this I in our tree level? Well, first of all, is it visited? No. Is it in our tree level? No, it's not. So we just skip it. We can, at this point, we've visited it, but we can skip it because it's not there. It's not in our tree level. And now we want to explore the next clockwise neighbor of our S node, right? Which is this diagonal right neighbor. But we don't want this I to be marked as visited because we're no longer going through this top branch. We're going through this sort of top diagonal branch, right? And you can imagine there might be a string in our list of words. That would be this Li. This could be a string. And this would go like this, right? So just because we already did this I, We don't want to keep this I as visited because for this particular branch of the algorithm where we go down to the L, it is not visited. Okay, so what that means is that in our code where we implement our depth first search, after we finish sort of exploring all the neighbors of a node, we want to unvisit that node, mark it as unvisited. Okay, literally just a Boolean flip. And this will be a lot clearer in the code implementation, but that's how we're going to do it. Okay, and again, during the code implementation, I think it'll be a lot clearer how that works. But here, just look at sort of this visual representation of how it works. So the next, let me undo all of this. The next neighbor is this L. Is this L in our tree level? No, it's not. So we skip it. We keep going clockwise. Is this P here in our tree level? No, it's not. Is this M in our P level? No, it's not. And by the way, here you'll notice that we're going clockwise, right? Like this. What we're probably going to do in code is we're going to probably grab all of these neighbors and dump them in an array, and then just recursively call some kind of explore method on them one by one, right? So we'll start by this one, like it'll be a for loop, like first this one, then this one, then this one, then this one, then this one. So like we won't need to keep track of the ones that we've already done. We'll just kind of naturally go in this order, which might be clockwise, doesn't have to be clockwise. It depends how we add the neighbors to the how we kind of traverse the neighbors. So finally, we get back to this I here, right? Because this I here is a neighbor. It's the left neighbor of our S. But the first thing we'll do is say, oh wait, is this I visited already? And yes, it is. In the branch where we started at T, went to H, went to I, went to S, we cannot go back here. Like, we cannot go back here because it's already visited in that branch. So because it's visited, we're just going to kind of like skip that. And now we're done. We're done exploring all the neighbors of our S in this branch. Like, we went from T, H, I, S, and then we explored all of the neighbors that were unvisited. There was one that was visited, so we skipped it, and we couldn't find anything. So now we backtrack. So we undo the visited, right? So visually, this is what matters. Like in the code, we're going to flip a Boolean now that we've explored all the neighbors. And here, the visualization of that is literally undo the visited. Undo the visited S. So we're no longer exploring S. And so now we're back at this point where we had explored T, H, and I. If you remember, at this point, we had first started with S, but then we still had P, M, I, and H as other neighbors. So we're doing the same thing now, right? We're going to say, okay, we've explored S. Now let's explore P. Is P at this level at THI? By the way, we have to also somehow keep track of the tree level, and this will be a lot clearer in code. It'll kind of be like this recursive beauty of a code implementation. But so, is P in this level? No, it's not. Skip it. Is M in this level? No, it's not. So skip it. Is I in this level? No, it's not. So skip it. And then we go to the H. Oh, wait. H is visited already. So don't even check if it's in the level. Just skip it. Okay? And then the key thing, right? Undo the visited. We were in this branch, TIH, undo the visited. And now we explored this I. We have to explore M, I, S, and T to see if these are in the tree level that we're at here, TH. Okay, so clearly M is not. Then we get to this I, and I is, right? So I is, whoops, let me undo that. So circle I. And then now we explore, like, we dive deeper into this. So now we mark this as visited. Whoops. Mark this as visited, right? So now we have to explore this branch. So now we have to grab all of the neighbors of this I and explore them. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. We're going to have 8 neighbors. So the let's start with the top left one, or top right one. So this I, there is no I here, so we skip it. And do we mark it as visited? No, we don't have to mark it as visited because we just skip it. Then we move on to the next one. This M, is it here? No. X, no. X, no. B, no. S, yes. We've got an S. Okay. And then we've got a word, this, and we add it to our final words array. We don't want to duplicate it, so we're probably going to keep track of words that are actually contained in the boggle board in a hash table, but that's an implementation detail. And then we keep on going, right? Now we're gonna start exploring all the neighbors of this S. So to be honest, this S here we have to mark as visited, and we're gonna explore X and B. All of the other neighbors are already visited. And eventually we'll start to get back. I'm gonna undo all of these stuff. Eventually we'll get back to the H. We'll mark the H as unvisited, and we'll move on to the second neighbor of the T, which is going to be I. So we'll already have done everything this way, and now we'll do everything this way. There will be nothing, and then we'll do this way, and there will be nothing. And then finally, boom, boom, we'll undo the V of the T, and we'll move on to the next character in the boggle board. And we're going to keep doing that line by line, character by character, until we reach the end of the boggle board. Okay? So before we dive into the space complexity and time complexity of this algorithm, I want to go through one last quick example to show you how this works out when we have repeated characters. So eventually, we're going to get to a point where we're at this R. Right? We're going to have traversed through all of our boggle board up until this R. We'll get to this R and we'll say, is R in our tree? And it's going to be, because we've got an R here in repeated. So if this repeated word is in our tree, then, R will be good. So we're going to mark it as visited. Then we'll go to this E. Is E there? Yes. E is in the level of the R node in the tree. Mark it as visited. Then we'll go to the P, E, A. Okay. Now, what is this A going to do? This A is going to say, okay, let's visit everything around me. So it's going to visit, the D, the R, the X, X, X. It's going to skip this E because it's visited, the D, and then it's going to go to the T. T is going to be there, right? Repeated. And then what is the T going to do? Let me undo, I guess, all the green. So what is the T going to do if we're going to mark it as visited? We're going to explore this. This is going to be visited. This. And this is going to be visited, right? This is what we would want. We would want another E, right, for repeated. But this E is already visited in this branch, right? In this particular branch, where we go, let me do it in brown, where we go like this E has already been visited. We cannot go back to it. And so that's how, with this algorithm, we're going to be able to avoid wrongly or erroneously marking a word like this repeated word here as a word that's contained in the boggle board by keeping track of these visited nodes in the algorithm with an auxiliary data structure, an auxiliary matrix. Okay, so that was a lot to cover. Let's actually dive into the complexity analysis now. So let me grab our words here and make them smaller to give myself a bit of space. So we've got the time complexity and we've got the space complexity. I'm probably going to need a bit more space for that too. So first, the space complexity. What are we doing with the space complexity? Well, we're building a tree, and the tree is going to contain contain all of the words in our list of words, and all of those words have, at most, S characters, where S is the length of the longest word. So we know that we have at least WS, where W is the number of words and that we're given, and S is the length of the largest one. We have at least WS auxiliary space for that tree. If you're not convinced of this, you can look at the suffix tree construction video on the website where we explain this. We're also building an auxiliary matrix that is going to contain all the booleans, true or false, of whether or not a node has been visited in the current branch that we're traversing. So we know that it's going to be WS plus, let's say, NM, where N is the width of the matrix and M is the height of the input matrix. Is there any other space that we're using? Well, we're also, returning a list of final words, but that's not going to surpass. That's going to be 2 WS. So that's not really going to do anything. We might be storing our final words in a hash table if we don't want to duplicate them, but that's not going to do anything. And lastly, we're going to have recursive function calls, right, as we kind of explore through the boggle board. But you can imagine that we're never going to have more than S function calls, recursive calls on the call stack at once, because the longest string or the longest word that we're given has length S. So at most, we'll have S recursive calls on the call stack. Let's go with the longest word here, which I think is not re-peated, right? We're going to have not re-peated, and this is the longest that we're ever going to go on the call stack, right? After we might go to the X, but then we'll go back. We might go to the O, but we'll go back. T, go back, right? And then eventually, we'll go back to the E, then we'll go back to the T, right, and so on and so forth. So the longest, the most number of calls on the call stack, or frames on the call stack that are going to be taken up at once, is going to be S, where S is the length of the longest word in our list. Why did my M get erased here? So this is going to be the space complexity, WS plus NM. Now, for the time complexity, it's going to be a tiny bit more involved, right? We've also got WS because it takes WS time to build our tree, right? We have to iterate through W words, and these words have at most S length or S characters in them, and we're iterating through all those characters to dump them in the tree. So that's WS time to build the tree. Then we know that we're iterating through the entire matrix, right? And because the matrix has, width N and height M, and we've got a total of NM nodes that we're exploring. Okay, so WS plus NM, but there's definitely more to this algorithm, right? Because for every node that we explore, for all of the NM nodes that we explore, we then go through all of their neighbors, right, to try to construct a string. Then for every one of their neighbors, we go through all of their neighbors, right? We go through THIS, then we go through THIM, we go through I messed up, right? So we have TH, we have TI, we have TS, then we have THI, THM, THI, THS, right? Then we have THIS, THIFP, right? We've got a ton of neighbors, right? For every neighbor, we've got more and more neighbors. So how do we analyze this from a time complexity point of view? Well, how many neighbors does one node have? At most, it has 8 neighbors, right? If you're a node in the middle here, you've got 1, 2, 3, 4, 5, 6, 7, 8 neighbors. If you're in a corner, you might only have 3 neighbors, or if you're in the top row, or a row on one of the outlines of the matrix, you might have fewer neighbors. But most nodes are going to have 8 neighbors. At least that's the most amount of neighbors that they have. So for most nodes, we're going to be exploring 8 neighbors. Again, granted, some of the neighbors might be visited in a branch and everything, but we're going with the worst case, right? So for most nodes, in the worst case, you're going to have 8 neighbors to explore. Then for those 8 neighbors, you're going to have another 8 neighbors to explore. Then for those 8 neighbors, you're going to have another 8 neighbors to explore. So what does that tell us? Well, we're multiplying 8 by 8 by 8, right? We're doing 8 multiplied by 8 by 8 by 8 by 8. At what point do we stop? At what point do we stop? Well, we stop once we've reached the farthest we can reach. And what's the farthest that we can reach? We said it when we were talking about the space complexity and the recursive calls on the call stack. We're at most going to explore S letters away, right? Because the longest string in our words, not repeated here, has S letters. And so we know that if we ever reach that longest string, like down here, let me write it in green. If we ever reach this longest string, so this is S letters here, at this point we're gonna stop exploring. We're gonna explore one other level of neighbors, but then past that, because they're gonna be like there will not be another level in the tree. We know for a fact. We're gonna start going back, right? So in other words, the worst case is going to be 8 times 8 times 8, and this a total of S times. So how do we write that mathematically? Let me erase this. It's going to be 8 to the power of S. 8 to the power of S. So what that means is, let me give myself a bit more space here. Let's grab this and move it a bit like this. So it's going to be W S plus NM multiplied by 8 to the power of S. And that is going to be our time complexity. Really in the worst case, because of course in practice, a bunch of our nodes don't have 8 neighbors, they have fewer than 8 neighbors, and then a bunch of our nodes have at least one visited neighbor in the current branch that we're at, probably more. Like for instance, you look in the bottom example here, this not repeated, right? When we're going to be at this T, for instance, literally all of its neighbors are repeated. Like R, E, hyphen, and A are not repeated, are visited, right? So in practice, it might not always be 8 neighbors, but we're trying to make this sort of the worst case time complexity and generalize it. So this is what it's going to be. WS for building the tree, and then NM times 8 to the power of S. Okay, that was a lot of stuff. Like I said, this algorithm is hard. Let's dive into the code walkthrough to see how really clean and elegant it actually looks. All right, so we've got our boggle board function defined. It takes in a board, which is going to be a matrix of letters, and it also takes in words, which is going to be a list of strings. And I've got a bit of code here already written. I've got this tree class defined, and it's got an add method, which basically adds a word to the tree. Now, you'll notice that in the last line of this add method here, we actually store the word, or rather we map the end symbol in the sort of last level of the tree that we're at to the actual word. And this is going to allow us to easily access the word without having to sort of keep track of it as we're traversing through the boggle board. And it'll make more sense as we implement the actual rest of the code. I've got another method already written out. The reason it's already written out is because it's really annoying to write out. And in fact, if you were in an interview, I would highly encourage you to ask your interviewer whether or not you'd actually need to code it out, because it's a pretty simple function. So it's called get neighbors, right? You pass it in the board as well as indices of a position, and all you do is you get the neighbors, the up to 8 neighbors of this position. The reason it's so involved is because you kind of have to check if any of the 8 neighbors are invalid, right? Like if you're in the top row, or if you're in the top corner, or rather, if you're not in the top corner, then you can append the sort of diagonally top left neighbor. Otherwise, if you are in the top left corner, then you can't append that neighbor. You don't have that neighbor, and you don't want to get an error in your code or get some kind of undefined value in your code. So you have to do these checks. I've written this already. If you were in an interview, like I said, you'd want to ask your interviewer whether or not you have to write this. They would likely say no. Anyway, getting into the actual meat of this algorithm. The first thing that we want to do is actually create and populate our tree, right? So we'll say tree equals a new tree, and then for word in words, we're literally just going to call our add method in our tree, right, that we have down here, passing in every word. Okay, simple enough. So this is like half the problem, right? Creating and populating the tree. Then we're going to initialize our final words, which at first is going to be a hash table. The reason it's going to be a hash table is because, as we saw in the example during the conceptual overview, you might have words that appear multiple times in the boggle board. Very likely you'll have words that appear multiple times. And so you don't want to have to, keep track of an array of final words and have to iterate through that array to see if you've already included a word or not. All you can do is store them in a hash table where, you can only have one unique, every word can only appear once in the hash table. And then at the end, you return just a list of the keys in that hash table. So then we want to initialize our visited matrix. This is going to be the auxiliary matrix that keeps track of whether or not nodes are visited. So the visited matrix is going to be identical to our board, except it's going to store booleans. So it'll be false for letter in row, for row in board, right? So for every row in the board, we create an array, and for every letter in every row, we just map it to false at first because everything is not visited, right? So false is going to mean not visited. And then we can start traversing our entire board. So we can say for I in range len of board, for j in range len of board at index I. And here we're going to make a call to a helper method, which we're going to write in a second. We actually explore, right? We say for every node in the board, we're going to explore. And we're going to dive off into some kind of, fancy recursive function. And then at the end of this for loop, we can just say, let's return a list of final words dot keys. So of course, this is in Python, but depending on your language, you might write this a bit differently. In JavaScript, you'd probably do return, object.keys of final words. Remember, final words is a hash table, and we want to return a list of the words, of the final words. So, okay, this explore function, what is it going to look like? Let's define it. Explore, we're likely going to take a position, right? So the indices that we're exploring. We're going to take our board because we're going to need to access letters in it. We're probably going to take a tree node, right? Because we want to see if a given letter is in our tree. And we're going to be updating this tree node to kind of determine what level of the tree we're in. And we also want to take in the visited array because that's going to tell us if something is visited or not. And finally, we want to take in the final words, right? Because the final words are going to be the thing in which we're storing a word if we ever come across, a valid word in the boggle board. So if we go back to line 9, here we can pass in I, j, board. We can pass in the root of the tree. So if you look at the way the tree is constructed, we've got a root property here, which is, the root level. And it's just an object, right, or a dictionary or a hash table. So we can pass in the root, and we can pass in visited and final words. Okay, so now what does the explore method look like? Well, the first thing that we want to do is check if something is visited. So if visited at index I and j, or indices I and j, then we return. you'll notice that our getNeighbors method does not only get unvisited neighbors, right? We could have implemented it such that it would only get unvisited neighbors, but we have this check here, so we don't really need to do it, right? And you'll see where getNeighbors actually gets used afterwards, but here at the top of this explore method, we have the sanity check that will always, return if we are exploring a visited node. Okay, so then we can say, okay, let's grab the letter that we're currently exploring at this board. So letter is going to be board at index I and j. And of course, by the way, you could call this a character, car if you wanted to. For the sake of this example, we know that we're only going to be given like letters in the English alphabet. But so now we want to check, is this letter actually in our current tree level? So if letter is not in our tree node, then we might as well return already, right? If we're ever at a point like when we were exploring the word this, right? And we were at THI, and let's say we explore a fourth letter that's X. If X is not in the tree node, might as well return. We don't even need to mark it as visited at this point because like we're done with that side. We're done with that part of the branch. But if it is in the tree node, right, then we have to do a couple things. First thing we want to do is mark it as visited. We want to say, okay, this node, we're actually going to mark as visited because we're going to further explore down this path, right? We're going to further depth first search down this path. Also, we want to update the tree node level. So tree node is going to be tree node at the letter, because the letter clearly is in the tree node, so we want to update that. Now we want to do another check, which is, do we actually have a string at this point? So is our end symbol, so you'll notice that our end symbol at the bottom here in our tree class is this this little asterisk, and this could be anything, right? You could make it a question mark or whatever. You'd have to make it something that is not going to be an actual letter. So this would be like a very small detail to point out to your interviewer that would show attention to detail. But so if your asterisk is in the tree node, then that means that you've got an actual string, so you want to add it to your final words. So final words of, and here you need to, because here we're basically saying final words of your word, right? Or like valid word is going to be equal to true. How do we access the valid word? Well, we can just say tree node at the end symbol. Because again, here on line 54, we actually store the word in the end symbol. So if we ever have an end symbol, then we know that the word stored at that end symbol is a valid word that we've clearly found in our boggle board, and we want to add it to the final words. And now we finish this helper method with just a few more lines, which are kind of the crux of it, which is we get the neighbors and we explore the neighbors. So we say neighbors equals get neighbors, and we literally just call the get neighbors method, passing in I, j, the board. And then we can say for neighbor in neighbors, we're going to explore that neighbor, right? So explore, pass in. We know that the neighbors, what do our neighbors look like? Our neighbors are arrays of length 2, where we have the I index and the j index, in the 0th and 1th position of these arrays. By the way, these could be tuples in Python. Probably they should be tuples in Python, but in all other languages, they would likely be just arrays, right? So here you can say explore neighbor at index 0, neighbor at index I, because remember, explore takes 2 indices at the beginning, right? I'm sorry, not index I, index 1. Then you pass in the board, and then you pass in the tree node that you're at. So remember, like your tree node, you have updated your tree node to be tree node letter, right? So you pass in this tree node. So you're probably one level further down, pass in the visited array or matrix, and then the final words. And that's it here. Or no, that's not it. That's not it. So it's almost it, right? We've done all of this, right? So if we recap, we've checked if something is visited, check if it was on our tree node. If If it was, then we could actually visit, update the tree node level, go further down, check if there was a string, get all the neighbors, start exploring them in a sort of depth first search way. By the way, you can imagine that, like, if we do a for loop, right? Imagine we've gotten the neighbors here in a clockwise order when we appended them. I don't know what order I picked for the neighbors here. I think I picked kind of an arbitrary order, but if it were clockwise, because of this for loop, you'd explore them in a clockwise way, right? And you'd do depth first search because you'd call explore recursively on the first neighbor. And before you'd ever get to the second neighbor in this for loop, you'd go through all of the explore method on the first neighbor. And then for that first neighbor, you'd redo a for loop through all of its neighbors, but you'd start with the first neighbor, and then you'd go all through again, right? So it's a depth first search. But so the last thing that we have to do here is after this for loop, after we visited all the neighbors, right? So here, let's say, for the sake of this example, let's say that here we've explored T, H, and I, okay? And now these were the three first letters in our example, right? And now we had, I think, an S to the right. And then here, let's say, we had like X, X, or let's say X, Y, Z, K, right? So we explore the S, then we're going to explore the K, then we're going to explore the Z, then we're going to explore the Y. These are all the neighbors. Then we're going to explore the H, and H is going to be already visited, right? And so then we're done with the neighbors. We've explored all the neighbors of T, H, and I. Sorry, all the neighbors of I coming from T, H, I. So now we want to, if you remember from the conceptual overview, we want to undo the visited of the I, right? Because we want to go back now to TH and explore all of the neighbors of TH. We started with I. We want to do Z, Y, X, etc. But when we do Z, we want to potentially re-explore I above, right? We want to do TH, Z, and then I. So we want to unvisit I. How do we unvisit I? Literally, just here, we do visited ij equals false. And that's it. Just like that, we've like undone the visited of I for the branch that we were at, which was th. Okay? And so here, I'd encourage you to like pause the algorithm if you're confused and to really kind of try to do like a manual example and go through all the recursive calls and how it would all work out. I sort of already did this just now and also during the conceptual overview, so I'm not gonna beat a dead horse at this point. But if you are still confused, do it yourself. Like walk through this code with an example, a small example, and you'll see how beautiful this line 25 is. Like how it beautifully works with the fact that this is a depth first search traversal and implementation of this algorithm. And so that is it. Like at this point, that's the algorithm, right? You create your tree. You create this visited array that's marked as false at the beginning. You iterate through all the nodes in the board, and for all of the nodes in the board, you call this explore method that goes through all of these like branches of traversal. And eventually, you get back to the first call of explore that was called on line 9. And on line 25, you set it back to visited equal false, right? So for like that first letter T in our matrix, you call explore on it, you do a bunch of shit, you mark it as visited and everything, and eventually you'll hit line 26 now, which was line 25, and you'll unvisit T, and you'll move to the second value, or the second letter in the boggle board. So this algorithm runs in, what did we say? We said nm, because we're traversing through nm nodes in the board. N is the width, m is the height. N width, m height of the boggle board. Times, we've got 8 neighbors at most. to the power of s, where s is the length of the longest word, because for every 8 neighbor of a node, we have 8 more neighbors, and then for all of those 8 neighbors, we've got 8 more neighbors and 8 more neighbors, but we're going to go at most through like s waves of 8 neighbors, because the longest word is going to have length s. Plus ws, because it takes us ws time to build up our tree, where w is the number of words, and s, again, is the longest word here. This is going to be the time complexity, and the space complexity is going to be nm, because we've got this visited array, plus ws for the space complexity of the tree. And like I said, the recursive calls, we have at most s recursive calls at once, because the maximum length of the word is going to be s. So that's not really going to affect our space complexity here. The call, the frames used up on the call stack. Okay, so that is it for this problem. Like I said, tough problem, like a really difficult problem, but it's super cool. It really mixes a bunch of different concepts and data structures and cool things, and you end up with this really, really elegant solution that just kind of like works. Hopefully you found this video helpful. I know it was a long one. I'll see you in the next one.